I think we can start. Good morning. Is that Mr. Frade?
Good morning. Good morning.
Hi, good morning, everyone. Hope you all had a good weekend. Well rested.
Yes, it is.
Good, thank you. Okay, well, there's still some people in the waiting room who will join us. I think in the next 5 or 10 minutes we'll be welcoming some more participants. But I think it's time we start. There's two subjects that I'd like to discuss today. That's on the one hand energy demand assessment, and that's specifically to companies and industry. And secondly, there is an assessment of bioenergy resources. That's the second part of today's session. I'm afraid that I don't have a co-host today, so I might be interrupted from time to time to admit people and mute them. Let's see how that goes. So energy demand assessment. Like I said, for today, for this part, we are going to look at industrial energy demand rather than, let's say, overall energy demand. I believe that Paul is going to be looking at energy demand for grids, for mini grids, and that is somewhat different from that of individual users, as you may be aware. It's quite situation specific, and it really needs to be assessed on a case-by-case basis. If we are looking at the energy assessment of companies, we're looking on the one hand on the energy consumption itself, let's say the kilowatt hours per day, per month, and per year, because that has a direct relation with the amount of biomass that is required for the energy production, regardless of the technology that you use. There will be a direct connection between the two. What is important there is the specific energy consumption related to the production output of the company or the industry, and we can express that as the kilowatt hours per ton of product. And in many industries, you'll also find quite substantial variations, seasonal variations specifically, related to the availability of primary materials for processing. What is important, of course, secondly, is the expected load, the average and peak loads in kilowatts or megawatts, because that will eventually determine the required capacity of the energy production equipment. All the installations will need to meet the required loads. And it's important to realize that the scale and the loading rate of installations have a large effect on the overall efficiency, and that in turn efficiency has a very large effect on the consumption of bioenergy feedstock. And we've seen that in earlier sessions looking at generators. Let's say the larger generators, let's say from a few hundred kilowatts upwards, will have a relatively high efficiency of let's say roughly 40% or more, and smaller generators can have a maximum efficiency that is considerably lower, say 35, 30, even 25% for the smallest generators. And in addition, if you operate a generator at a low loading rate, then the efficiency may be lower still. Now, before we start looking at the actual demand assessment, see that Carlos has joined as well. I will make you co-host. I'll try that. Okay. It's important to start with a good insight of the different production processes that are taking place in the industry that you're looking at. So getting a good idea of the material streams, so raw materials. In this particular drawing, you'll see let's say 2 streams of raw material going in. This is just, you know, an example. This could be anything. So there's this raw material going in. There's energy being consumed, often electrical, but also thermal. Let's say heat, often in the form of steam. And then, you know, from one process, the output goes to the next process where you have another type specific energy consumption, and goes on to different other process. In the end, you have one or multiple outputs. This kind of insight really helps you in identifying what are the main energy consuming steps, and what kind of, let's say, heavy equipment can you find in which of the processes, because those might be interesting to focus on, not just for the determination of loads, peak loads and average loads, but also for the production of byproducts in the end, that could be used, for example, for energy generation. Note that I also included the thermal energy here. So the previous sheet, this looks a bit like it's focused on electricity, because I'm using kilowatt hours here, but it also holds true for heat consumption. Heat can also be expressed in kilowatt hours, although more usual would be, for example, gigajoules per hour, per day, or per ton of products, or tons of steam. So getting to know the process is very important. Also getting to know the production regime. So let's say how many shifts do you make in a day, how many hours per shift, how many days per month, and how many months per year. And that will of course also show the seasonal variation that you can expect. So the first thing that you can do when carrying out an energy demand assessment is to make some first projections. And that can be done broadly using 2 types of information. On the one hand, it's quite often it's possible to find some indications in literature. If you look for specific industries, you can find indications of, you know, the electricity consumption per ton of product, or the heat consumption per ton of product. And if you then have some information on the scale of production of a certain company that you're going to look at, then you already get some first indication of what will be the scale of the energy demand. It is often dependent on the location and the scale and the technology. You see, for example, here that there's some range indicated for the energy consumption. That is because these figures here, for example, they include also, you know, smaller and bigger plants, sugar plants, and plants in I think in Australia and India, and I think it's in total it's 8 or 10 different plants where this information is taken from. Secondly, it's possible if there's some information that you may have from similar industries. So let's say from earlier studies in, for example, sugar industries or starch processing industries or cashew processing industries. Then these figures can also serve as a first indication. The same holds, of course, that it's location and scale and technology dependent. So it's important to realize that there will be deviations from what you may find during the actual assessments. The way it works, if you have indications from literature, for example, on the specific energy consumption per ton of product, as shown in the previous table, and you have indications of the factory production process, the tonnage per day of output, then the first step, of course, you can make an estimation of the energy consumption per day in kilowatt hours. Then you can continue if you have an indication of the working hours per day of that factory. That is, you know, something that you can quite easily get by just making a call and asking some first questions. Then you can quite easily arrive at an indication of the average load of the factory. Let's say it's basically the amount of kilowatt hours per hour, and that is a principle that equals the average load. In a similar way, you can derive what could be the energy consumption on a monthly basis, if you know the monthly production output of the factory. Important to realize the seasonal variation. So knowing what are peak months, what are low months, and in what months there's no production and no output. And of course, in the end, also for the annual output, which will give you to some extent the factory consumption on an annual basis. So literature values as a benchmark. When you go visit the company, let's say interviews are, let's say, the first source of information, the first means of data gathering for information. It's of course important to find the most knowledgeable person, so persons who actually know something about the energy consumption of the factory, who knows the installations, who knows perhaps the figures that are collected, the data that is collected on energy consumption. Secondly, it's very important to make sure that the person that you talk to as a solid basis for the information that is collected. And it's not just, well, if it is his estimation or his feeling, for example, that you know that this is the basis of the information that is given, or whether he has, you know, for example, any measuring equipment installed that he takes the information from. That means that the strength of the information is much higher. The second source of information is documentation that is typically found in companies. It helps a lot, of course, if there's electricity bills from a company that is connected to the grid. It will give you at least the amount of kilowatt hours consumed per month, and in many cases also the maximum kVA that is used by the factory in each of the months. Second good source of information is the consumption of fuel, as will be seen on fuel bills. It is important, especially for diesel, to know what amounts are used for energy generation and what amounts are used for vehicle use. So often it's just one fuel bill, it's one reserve, and then you know, if fuel is used for both, then you should get an indication of what is used for energy. If you have this information, try to match it with the monthly production data, so that in the end you may get your information in consumption per ton of product, and it will then also help you making projections for other months that you may lack the information from. So let's say if there's peak months with peak energy consumption and peak factory production, then you can arrive at a certain kilowatt hours per ton of energy consumption. If you then have months with lower production, then you can make some assumptions on the reduced energy consumption. Furthermore, important is to have an overview of the equipment that's used. Electrical equipment, but can also be, let's say, heat consuming equipment or heat producing equipment, so that you have an idea on the one hand what amount of electricity is produced internally, and what are the major consumers. And in some cases there may be energy auditing reports available if there have been specialists that already have been looking at the energy consumption in the company with the aim of proposing for example, energy efficiency measures. Then such reports can give a wealth of information that you can use for your own estimations. Well, I think I explained these steps. If you have your energy bill showing your kilowatt hours per month, then you directly have this consumption data. In combination with the factory output, you can get specific consumption kilowatt hours per ton, which in combination with the daily output or the annual output can give you information on the say the daily or the annual or the daily factory consumption. It's good to understand that if you have variation in daily outputs, that you may arrive in the end at let's say maximum daily energy consumption also, so that you can see if there's a large variation in that as well. And then again, as we saw in the previous schedule, if you know the amount of the number of working hours per day, then you can arrive at your average load at the factory. And then again, if there's an indication of the maximum kVA consumed at the factory, then this will give you your indication of the maximum load. Furthermore, observations are important. If we look at the different steps, different processing steps in the factory, looking at equipment that's installed, let's say production equipment, and especially looking at the larger motors, because they can be the large consumers, and especially also the elements that's really cause the high consumption peaks. If you have large motors and you don't have any soft starting equipment, for example, then you can have very high startup peaks of large motors, and that can, to a large extent, determine the maximum kVA of your factory. It's important to know if there's transformers or backup generators. What is the capacity of those? As that will give you an indication of the required generation capacity of your energy production system. And if there's any borders, have a look at plates that maybe they're showing the capacity. Let's say either in tons of steam per hour or in kilowatts, megawatts. A fourth method of data collection is, of course, making your own measurements, and I think that is one of the most important ones to get really quality and precise and reliable data. What you can do on the one hand is carry out spot measurements. If you have a multimeter, preferably a multimeter with let's say a function that can actually measure the power consumption and the power factor. Otherwise, you may be stuck with just doing the current measurements, and that may only give you the parent power, so the kVA rating, and not so much the active power consumption, the kilowatt rating. With a multimeter, it's quite easy to check the inrush current of the larger motors. If you have access to the cabling and the terminals of the engine. If you have a power logger, so one that can take measurements, for example, every second, and store them, measurements of current and voltages, and log those over a longer period of time, then that can give you a very accurate indication of the overall consumption and peak loads of your factory. So this will give you the trying to mute Mr. Senda. Noise coming from somewhere. Okay, thank you. So that's a data logger. When you do measurements, it's of course very important to know exactly what it is that you're measuring. On one hand, that's knowing whether you're actually measuring the active power or the apparent power, kilowatts or kVAs. Like I said, if you're using a clamp-on meter, just measuring the currents, then the only thing that you can calculate afterwards is the kVA. Whereas if you have a unit that can also let's say measure the voltages at the same time and use it for active power measurements and power factor measurements, then you can also know the kilowatts. Often, if you go to larger factories, you may find in the switch room it's a different let's say outgoing lines to different departments of the factory, and then it's very important to know where to place your equipment so that you actually know so what part of the factory you're measuring. And of course, it is important to be aware of the number of phases that are in use, and whether you're looking at a balanced three-phase system, or whether there's large degree of imbalance. Especially again, if you're working with a multimeter, it's very important to check the currents in the three phases, and not just in one, under the assumption that the three phases carry the same current. For off-grid systems, it's sometimes possible to measure the diesel consumption on say usually on a daily basis or a shift basis. And if you then also know the generator capacity, then you can let's say calculate what will be more or less the loading rate of the generator, and therefore what is more or less the efficiency. And the efficiency in combination with the diesel consumption will give you an indication of the overall production. So it's possible, if you manage to measure the output of the generator, for example, with a power logger, and you can also measure the generator diesel consumption. You can verify the two figures and determining whether the generator is actually performing as can be expected. So this is how measurement data could look like. Let's say basically, if you have your kilowatt hours measured, for example, over a shift or over a day or over a number of days, then you can calculate the specific energy consumption, which then, in combination with the production per day, per month, or per year, will give you the kilowatt hours per day, per month, and per year. And the measurement itself will give you knowledge on the maximum load and the average load of the factory. The way that you can analyze the consumption data, the fuel consumption data of your generator is as follows. if you have your liters per day consumed, and you combine it with the kVA rating of your generator, you can estimate the kilowatt hours produced during this period, day in this case. Combine it with factory production in tons, and then you get your factory production in tons, in kilowatt hours per ton, and then you can again calculate the daily consumption on the basis of the amount of products that is produced on a daily basis, on a monthly daily basis, or an annual basis. And in the end, if you have the information on the working hours, then you can calculate the average load. So that was more or less electricity. Looking at heat, you may find more or less the same steps that you can use for gathering the information that you need. On the one hand, there's literature, indications of the heat or the steam consumption. Secondly, look at the different processes in the factory and the data that may be available from the company, such as let's say fuel consumption, or actual measurement data of the steam production and steam consumption. And then there's measurements that you might be able to do, although for heat it's a bit more difficult than for electricity in general. As indicated, make sure that you understand the production processes that are taking place. Get your overview of the inputs and outputs. Make sure to include the fuel consumption, the steam consumption, and or the heat consumption of the different process steps. I'd like to share with you an example from the Maragra sugar factory. We've seen that a couple of weeks ago when there was the presentation from a Maragra engineer. This was one of the sheets that he used to explain the different production steps in the factory, from let's say intake of cane with the quantity, preparation. I'm not sure what PI means in this case. I think it's the selection, maybe taking out some materials with a certain efficiency eventually. Then you have the sugar extraction, which will, let's say, the pressing of the cane, which results on the one hand in bagasse, so that's the pressed out stalk, let's say cane stalk. On the other hand, the cane juice, which then goes to the sugar extraction process, using sugar and molasses. On the other hand, the bagasse goes to the boilers, steam boilers, which produce steam used by the primary machinery, and that is, I believe, mainly for the pressing equipment. See that on the other sheet. And part of the steam goes to the electricity production unit, where the two turbines are installed, producing electricity with a maximum capacity of 10 megawatts. let's say the scheme might give some further information, for example, on the quantity of bagasse and the quantity of juice, the quantity of molasses produced, the quantities of steam produced, for example, and perhaps this is the capacity. I think what should be noted here is the actual output, the actual production in megawatt hours per day or kilowatt hours per day. But this is basically, you know, a schedule that gives you the basic insight in what is happening in the factory. Now this was the overview of the sheet that was presented. That will give you more information on the electricity and heat production side. As we know, there's the 3 boilers, each with the capacity of 41 tons per hour of steam, producing a total of roughly 100 tons per hour of steam. Which is divided over one group of turbines that drive the primary extraction equipment in the factory, and then there's the 2 turbines. There's the back pressure turbine, an output capacity of 6 megawatts, producing just under 5 in practice, and it will also give low pressure steam. And then there's the extraction the extraction condensing turbine with a capacity of 4 megawatts, producing condensate of roughly 10 tons per hour and producing low pressure steam of about 10 tons per hour. So we know here that the total amount of steam that goes to the factory is roughly 84 tons per hour to the process, and then the condense goes back to the cycle. And we know roughly what amount of electricity is being produced. And I have some questions for you about this. On the one hand, on the steam consumption. On the other hand, on the electricity consumption. And thirdly, how this compares to what we find in literature. That is, of course, referring to the tables that I showed earlier, showing the typical consumption of, let's say, sugar production processes, electricity and steam. So I don't know, Carlos, do you wish to add something in Portuguese on this? Do you think that everything is clear?
Well, I hope it's clear. I can maybe refer to the questions.
Yeah.
Em português. Bom dia, colegas. As questões são relacionadas com o material que foi dado há pouco tempo. A primeira pergunta é: qual seria o consumo de vapor por tonelada de cana usada na fábrica de Maragra? Primeira pergunta: qual seria o consumo de vapor por tonelada de cana na Maragra? E há 3 respostas propostas, não é? A linha A, B e C, qual delas é que é correta? Portanto, a linha A, 0,43 toneladas de vapor por tonelada de cana. A linha B, 0,39 toneladas de vapor por tonelada de cana. A linha C, portanto, 0,43 37. Depois temos a segunda pergunta. Qual seria o consumo de energia elétrica por tonelada de cana? Depois teríamos 3 respostas possíveis. 28 kWh por tonelada, portanto, consumo de energia 28 kWh por tonelada de cana, ou 37 kWh por tonelada de cana, ou não temos dados suficientes para fazer qualquer afirmação. A última, como é que podemos relacionar os dados que calculamos com os valores que vêm na literatura? Seria a linha A, os valores calculados muito elevados, a linha B, mas aqui vem C, mas seria a linha B, é muito pouco, portanto, elevado, baixo, e a linha C, dentro das expectativas, de acordo com a quantidade de cana que usamos. Bart, on question number 3, notice that you have A's. Yeah, okay.
Yeah.
Okay, it's okay. Okay. Ok. Então, colegas, façam favor. Roberto.
I'll give you a hand and
Yeah.
give you this sheet.
Ora, a imagem que estamos a ver agora provavelmente pode ajudar a pensar na forma de resolver o exercício, não? Os colegas têm o material que foi enviado, portanto podem, se quiserem, abrir no vosso computador esta página e ver este slide que está aqui.
I think it's B. Hello? I think it's number B.
B.
39, yeah, 39 tons per ton of cane.
Yeah. Alguém mais quer contribuir com alguma resposta? Mais alguém quer contribuir com alguma resposta? Para a linha A, para a primeira pergunta, temos uma resposta que diz que é 0,39 toneladas de vapor por tonelada de cana. Uma proposta. Não sei se haverá alguma resposta para a linha, para o ponto número 2, pergunta número 2. No, Bart, I think you can comment on number 1 while they are thinking on number 2 and number 3.
Okay, thanks, Carlos. Actually, the solution of number 1, we saw that the steam consumption was 84 tons per hour, and we saw that the cane intake was 230 tons per hour. And if you divide the two, then you arrive at 0.37 tons. So that's if we go back to the previous screen. It's a bit tricky. On the one hand, it says here exhaust steam is roughly 90 tons per hour, but there's about 6 tons per hour which is taken from the low pressure side out of the steam flow. So the total amount of vapor going to the of steam going to the factory is 84 tons per hour, and dividing that by the 230, that will give you 0.37. I don't know if there's anyone.
Algum comentário, colegas? A resposta correta seria a linha C, 0,37 toneladas de vapor por tonelada de cana. Algum comentário ou dúvida em relação a este resultado?
Eu gostaria de perceber melhor porque é que ele considerou 84 toneladas por hora e não 89,8 toneladas por hora.
Yeah, if you can go back to the previous slide, Bart.
Yeah.
The question from Fred is why you use 84 rather than 89.8?
Well, basically the let's say the total steam production from the turbines may be 90 tons per hour, but the actual consumption in the factory is 84, because part of the steam is taken back into the process. It's not actually used in the factory, so that's why it's actually 84 tons per hour that is being used.
Yes.
I should of course add that the difference is very small between 0.37 and 0.39.
Yes.
Let's say at this rate, I would say it's within the error range. But for the sake of the calculation, I would propose using the 84 tons per hour.
Yeah, can I also ask you a question? I also think you should have used 89.8 because the remaining tones are used to heat up the water at 80 degrees. Are you considering that as well?
Let's see. That is these ones. You mean these 6 tons?
No, the other one, reservoir of water. It has to be elevated to 80 degrees. Who is doing that?
Well, that's basically the temperature of the condensate.
Yeah, so you need to use that amount, 89, not 84.
Well, no, it's actually the heat that is still in the condensate. Let's say after the steam has has condensed, let's say the temperature is still at an elevated level. So basically, if it condensates at well, depending on the pressure, but let's say if it condensates at atmospheric pressure, then you can have, well, for example, up to 95, up to 99 or 100 degrees of water. So that is due to the heat that is still contained in the condensate. It's not that this is a water that has been cooled down to ambient temperature and then needs to be reheated. That's basically still the temperature of the condensate. It never goes below this temperature. I think that's. I don't know if this is. Is that what you meant, Mr. Vos? Mr. Kamal?
Yeah, I think some of the steam is used for heating up the water, and I think by using 84, you're not considering the whole cycle. That's my assumption.
Okay. Well, it could have been because I missed the Portuguese part of the presentation, of course. But let's say the way that I interpreted this scheme is that you know that this is actually being consumed, and that the 80 degrees is just the temperature of the condensate after the steam has been used in the factory, because it's a closed system. It's not like, let's say, new water with low temperature is being all the time added to the system. Although there will be some part, so some part of makeup steam that's always there, but that's really very small amounts in a closed system.
Okay, thanks.
Thank you. So then the electricity consumption. Anyone?
Podemos ver agora o consumo de eletricidade, energia elétrica.
Because the only data that we do have is 10 megawatts. If you are dividing this, we are getting a very small value. And I feel that the amount, I think the...
Hello?
I think that we can't.
Yes, Mr. Frade?
It seems that we lost Mr. Frade now.
Okay.
Hello? Mr. Frade? No.
Okay. Well, let's say the 10 megawatts Mr. Frade referred to, that's the actual production capacity of the combined turbines. That is indeed that information will not help us directly, although there is the information of the actual typical output of the turbines. That's the 4.9 megawatts of the back pressure turbine and the 3.5 megawatts of the condensing extraction turbine. So it gives us 8.4 megawatts, and on that basis we could conclude that we have let's say 8.4 megawatts divided by 230 tons, that will give us
36.
37.
37, yeah.
Yeah, 36.5, I believe it is. That's true. The only thing is, on the one hand, that's the production of the turbines, and we also know, although this information is not here in the diagrams, I believe, that some part of this is also shared with the local grid, and we're not quite sure what amount that is. A second thing, and that is important to know, is that we also have this part here, and that is not strictly electric, but it is, let's say, mechanical energy. And if you want to compare, let's say, different industries with each other, let's say the electricity consumption. Let's put it this way: in most sugar factories, at least most modern sugar factories, you see that all the equipment is electrically driven. So in order to make a comparison between factories that are completely electric and factories that are partly mechanically driven by steam systems, you also need to convert this mechanical energy to an electricity equivalent. And you can do that by using, for example, this steam model that we discussed a couple of weeks ago when discussing this case at Maragra. And you could see that this will give, let's say, roughly 2 megawatts of output. So that means that strictly speaking, you would need to add this to the 8.4 megawatts electric that is being produced in the factory, and then you would arrive at, let's say, roughly 45 kilowatt hours per ton. But as this information is not available, I would say it's overall it's insufficient to really calculate the amount of power needed in the process. Here again, you can say that the difference between 45 and 37 is not that big. At the same time, let's say if you compare it to literature values, let me back a little bit. No, this one. You see that the electricity consumption information is typically between, let's say, for those reference sugar plants, is between 22 and 45 kilowatt hours per ton of cane. I should add that this higher range also includes some of the mechanical power. That's similar to what we see in the Maragra case. And the steam consumption is between 0.22 and 0.58. So actually we see, going to question number 3, we can conclude that it's within the expected range of literature values. Any questions about that?
Alguma pergunta, colegas? Dúvida?
right. Well, I think it's time we move on. Otherwise, we get some time constraints in the next part. As indicated, considering the measurement of heat, that's often a bit difficult. The electricity, you can you can hang up, you can connect your measuring equipment, and that will more or less instantaneously give you your information. Whereas, let's say, directly measuring steam or hot water really requires information on pressure, temperature, and especially on flow. And although pressure and temperature are relatively easy to measure, flow is not typically something that is measured in factories. Let's say in the typical factories that you may be looking at. What is often possible is to make some estimations on the basis of the amount of fuel that is consumed for the production of the steam or the hot water, whether that's liquids, gaseous, or solid fuels, and combine that with an estimate of the efficiency of the heating system. In some cases, it's possible to measure that fuel consumption, especially with smaller systems. If you, for example, have liquids or solid fuels, it could be possible to do some physical determination of the quantities consumed. And in some smaller systems, you may find an open steam system. It means that steam is produced from fresh water continuously, and then the steam is vented into the open air. And in such a case, it's possible to measure the amount of water that is being consumed for the steam production, and therefore also consumed by the process in the form of steam. So that is the end of this part. I don't know if there's any questions.
Colegas, haverá alguma pergunta sobre essa primeira parte do dia 2? No questions, Bart?
Okay. I propose that we just continue directly with the next part. All right, so that's on the resource assessment, bioenergy resource assessment, looking at available feedstock resources, feedstock properties, logistics required for the
Bart, make sure that you display the PowerPoint. Not yet?
Yes, I do.
No, we cannot see it.
You can see it. Oh,
no.
Let me see just a moment.
Okay.
Yeah.
Yes. Now we can see it.
Okay. Thank you.
Yeah.
So looking at the available feedstock resources, quantities that may be available, the properties of the feedstock, the logistics required for the continuous supply of feedstock, and what may be considered for the validation of feedstock assessments. So the starting point for looking at the resource availability, on one hand, you have to look, of course, on what quantities of biomass can be made available. That can be, let's say, waste or byproducts from specific sources, like companies, processing factories, or let's say waste coming from a city or from a certain forestry area, for example. And this quantity more or less determines the maximum energy production, or let's say biomass fuel production that can be produced. Let's say apart from possibilities of adding other sources of feedstock to increase the total energy potential. And it's very important, of course, to know what kind of feedstock you're talking about. So knowing, for example, what is the moisture content, what is the heating value, so that you get a good overall view of the energy potential. On the other hand, there's of course the energy demand. Let's say, especially if you look at isolated systems, and you have a certain limited energy demand that needs to be satisfied, then it's possible that the amount of biomass needed to satisfy this demand is actually smaller than the quantity of biomass that is available. Or the required amounts are more than the available amounts, and that means that either additional quantities will need to be found, or let's say only part of the energy demand can be satisfied by the bioenergy production system that can be developed. So that's basically it. If the available amount of biomass is more than what is required, then you can choose either to use only part of the amount of biomass that is available. Second option is basically to find additional energy consumers so that you can increase the scale of production, and that might have, let's say, cost advantages, economies of scale, or let's say efficiency advantages because of the large scale. The other option, where the amount of biomass is less than what is required, then, as indicated, you can look for additional biomass resources to complement the amount of biomass that is needed. Or you can choose to cover only part of the energy demand. For example, operate your system in base load, and if the peak load is covered by other sources, for example, with diesel backup systems in a hybrid situation. It's advisable to get a first idea of the scale of your system, either based on the amount of biomass or on the energy demand. And it's a bit of an iterative process, or at least it can be. On the one hand, it's important to get an idea of what is the energy potential from the feedstock, and what kind of conversion options do we have for this feedstock. So whether it's, for example, a dry solid, or a wastewater, or another wet type of feedstock, that for a large extent determines what kind of conversion technology is available for it. Then there's of course the quantities and the energy demands that needs to be satisfied, and that determine the scale. And scale in itself also influences what kind of conversion technology options might be available. For example, talking about steam cycle systems, if your energy demand or your amount of feedstock indicates a limited scale of maybe a few hundred kilowatts or less, then, for example, this steam systems are not typically the best option to be considered. And let's say all this together will give you an indication for that feedstock under those conditions, what could be the conversion factor of biomass to energy. So how many kilowatt hours can you produce basically per ton of product? This is a small example for a rice processing factory. What you see with rice processing is the removal of the rice husk. This husk is it's a quite suitable type of biomass feedstock for energy, because it's basically it's dry. It does have a high ash content of on average about 20%. It's produced in quite large quantities. Let's say it's about 20 to 25% of the paddy rice intake. So for, let's say, 50 tons per day of rice processing, you will get roughly 10 tons per day of rice husk. And your electricity consumption for the processing could be in the range of about 25 kilowatt hours per ton of rice processed. So for such a unit, it could be in the order of 1250 kilowatt hours per day. So it might give you, let's say, roughly 100 kilowatts on average of electricity demand. Let's say on the basis of the feedstock and the typical electricity demand, you might be looking primarily at gasification. So combustion might be possible if you would be looking at the total use of the husk. And then if you would look, for example, at gasification for just meeting the demand of the factory, you could have an efficiency of roughly 15%. And then the question is, of course, what is the conversion factor that you might find here? I don't know if you are up to getting into some calculation work again. I hope you are. So that would be the question for this system. Could you give an indication of the conversion factor of rice husk to energy in this case on the basis of this information? Anyone?
Que temos mais algum exemplo? Mais um exemplo? Para calcular o fator de conversão da palha de arroz para energia. Alguém quererá contribuir? Pergunta número 1, qual é o fator de conversão? Convertemos a palha de arroz em energia, em quilowatt-hora. A conversão será linha A, linha B ou linha C?
Anyone?
No one?
No one?
Not yet.
Okay. Right, well, maybe at least for number 1 we should be maybe show the solution. Basically, looking at the rice husk itself, it has a net heating value, a net calorific value of 14 megajoules per kilogram, which is the same as 14 gigajoules per ton. Now, if you divide it by 3.6, you get the let's say the heating value in kilowatt hours, and that is about 3.9 kilowatt hours per kilogram. And then if you multiply that by the efficiency of 15%, and then you get 0.58 kilowatt hours per kilogram of rice husk. I don't know if there's anyone who has an idea on the basis of this answer, what would be the solution of question number 2? The amount of husk needed to cover the electricity needs of the rice processing facility.
Sorry, but
Yes, good morning.
good morning. Sorry, can you repeat the explanation, please?
Yes, basically, if you look at the rice husk, which would have a typical heating value, net calorific value of 14 megajoules per kilogram. You can convert this to kilowatt hours per kilogram of rice husk by dividing it by 3.6. So if the net calorific value in megajoules is 14 megajoules per kilogram, in kilowatt hours, it's 3.9 kilowatt hours per kilogram. And if you then multiply that, so that would be for 1 kilogram of rice husk, would be the amount of, let's say, chemical energy stored within. And if you then convert it to electricity with gasification, for example, then you could have an efficiency of 15%. So if you then multiply this 3.9 kilowatt hours per kilogram by 15%, then you arrive at the 0.58 kilowatt hours per kilogram of husk. Does that answer your question?
Yes, thank you. Yes, thank you.
Okay, thanks. So now that you're with us, Claudia, could you give it a go for a solution of question number 2? Jessica was.
Colega Jéssica, a pergunta agora é para si. Tem alguma ideia sobre a pergunta número 2, depois de ouvir a explicação da linha da pergunta número 1? Colega Jéssica?
Sim. Vou tentar.
Yeah. She will try.
Okay, good.
Será B?
Yes, I think probably B.
Okay, could you explain how you
Como é que
you got
chegaste à conclusão que pode ser B? Pode explicar? Colega Jéssica? Colega Jéssica? Okay, I think we can proceed, Bart.
Okay. Well, thank you. Anyway, the answer that you gave was correct. We were looking at a consumption, the daily consumption of 1,250 kilowatt hours per day. If you have a rice husk which could produce 0.58 kilowatt hours per kilogram, then you divide the 1,250 by the 0.58, and that will leave you 2.2 tons per day of rice husk. On the other hand, of course, if you produce 10 tons per day of husk, and you would need only 2.2 for meeting the energy requirements of the factory, then of course you can produce a lot more of energy from this quantity. And basically, if you would be using all of the husk rather than just the husk needed for the factory, you could have, let's say, the 10 tons per day multiplied by 0.58 divided by 24, then you may get a continuous output of 243 kilowatts. So that is solution, that is answer B. I think I'll need to proceed, otherwise we may get into time constraints. Sorry, I don't know if there's any questions on that.
Haverá alguma dúvida para a pergunta número 2 e número 3? As soluções foram dadas, a colega Jéssica respondeu corretamente e houve explicação. E a seguir foi a explicação da pergunta número 3, que é a linha B, a resposta correta é a linha B. Alguma dúvida? No, but I think we can proceed.
Okay, thank you. So looking at the amount of feedstock that could be made available, as with the energy consumption, it's very important to understand the processes going on in the factory, in the industry, so that you can better understand what kind of feedstock quantities could be made available, and what could be the properties of them. And on the one hand, looking at different processes that will produce byproducts or wastes. On the other hand, other processes that might be consuming a part of those wastes. Although it's possible that in the end, if, for example, energy production that is currently taking place using some of the waste can be taken over by a let's say a larger energy generation plant that could also produce the heat, for example, here. and the amount of waste that would be produced by the boiler could then be incorporated in the overall system. But that's all that requires a level of insight in the different processes taking place in the factory. So that's it basically. Getting the overviews of the amounts of biomass that are being produced per day, per month, taking into account the seasonal variations and the quantities per year. Having a look at the current internal usage, tons per day, or the percentage of the total quantities produced. Get an overview of the amount of byproducts of waste that is produced per unit of factory output. So, for example, for the rice mill, we saw that between 20 and 25% of the paddy processed in the factory ends up as rice husk. This is valuable information that you can, on the one hand, relate to what you find in literature, or on the other hand, you can use the literature information and combine it with the production data of your factory, so that you can arrive at an estimation of the quantity of biomass that would be available. It's important. Sorry, it's important to consider any projected changes of the processes in the future. So if there's, for example, any extensions of the factory being considered, then you should be possibly be looking for larger quantities of biomass that would be made available. On the other hand, of course, then the energy consumption could be increasing, so that those two should be looked at together. And what is important is what is currently being done with it. Let's say the current method of usage of the material or the disposal, and whether there's cost involved for getting rid of this material, or whether the material is actually sold and it has a value and it creates a source of income for the factory. It's of course very important for the financial assessment of the project. Important to realize that the data is not always available or very reliable, and it's always good to have different angles from which you approach the availability. On one hand, gets beforehand, before you start, get some indications from literature, so that you have an idea of what range the feedstock production should fall in. Second angle would be interviewing the owner, the operators, taking into account the reliability of their indications. If they don't have any means of measuring or weighing the quantities, then it's important to know how they know the information that they provide to you. making your estimations on the basis of the actual daily production, let's say the output of the factory, using data from production records of the factory, and combine that with literature sources, and lastly, maybe possible to do your own measurements, or let's say make observations in any case to get an idea of the order of magnitude of the amounts that are indicated from other data sources. For example, we were just looking at the Maragra sugar factory. We're looking at 230 tons per hour of cane intake. Indications from literature show that the bagasse production per ton of cane is let's say roughly 30%, ranging from about 26 to 34%. That would mean that the daily production of the bagasse at Maragra would be in the range of 60 to 78 tons per hour. And the information that we had from the factory was that the amount of bagasse, at least the amount of bagasse that was consumed by the boilers, was 48 tons per hour. And we checked with them, and what we understood was that they actually consume all of their bagasse. So this would actually also be the amount of bagasse that they would be producing. Now, if you have this indication, then it might be a point where you start asking additional questions to make sure that the information that you obtained is actually correct. So whether this figure is what you understood. If it is, then there might be discrepancies. For example, this figure of 230 tons per hour, that might be either the intake or the processing capacity, whereas maybe the actual intake of the bagasse might be lower than this. So that's possibly this amount of bagasse is the actual production, whereas the cane intake might be the intake capacity, meaning that the actual intake is lower, then you get towards a percentage of bagasse on cane that's more in line with what you find in other sugar plants. Yeah, and maybe other discrepancies. It is of course possible that there's in the end that a particular type of factory of process might be, say, more material efficient with better presses, or maybe even another type of raw material that might result in different output, different biomass production per unit of raw material. Well, I said, if you can manage to do measurements, then this can really improve the reliability of your estimations of biomass availability. And in some cases, that's measuring is the only way of obtaining the information that you need. if you do, then it's good to work together with operators. Options that you may have for measuring is determining the amount of feedstock that is produced in an hour or a full day, 24 hours or a shift, and then also relate this quantity to the amount of factory output, factory processing during the same period, the hour or the day or the shift. And if you do have this this information, then you can determine the waste production per unit of product, and then start combining this with production records. Let's say the production per month, for example, or per year, so that you can determine what would be monthly or annual production of biomass. Now the actual production of feedstock, meaning the purposeful growing of feedstock, other than what you might have if you consider byproducts or waste. That might be required if your energy demand is higher than what you can produce with the waste that you have. Let's say depending on the technology that you are considering, you can then start producing feedstock that can be combined with other types of feedstock. It could be, for example, wood, fuel for combustion, for gasification. For biogas, this could be, for example, energy maize. For bioethanol, this could be using cassava or sugarcane. And for vegetable oils or biodiesel, this could be different types of oil crops. If you consider this, then of course it's highly important to have good estimation of the yield that you can expect, the yield of these products, the properties, basically determining, for example, what is the quantity of oil that can be extracted from a certain crop. What's the quantity of sugar or starch that can be produced from a certain crop? What are the fuel properties of wood, for example, or what quantity of biogas can you produce per ton of maize in an anaerobic digestion system? The production cost, so that you can have an idea of whether it's financially feasible of producing this feedstock, and it might be required to have very specific agricultural or forestry expertise for this. Having specialization in the energy production, let's say the bioenergy production, is one thing, but the actual production, so the agricultural practices or forestry practices for producing biomass is a bit different. When you start producing bioenergy feedstocks, then you may be faced with higher financial costs, depending, of course, on let's say, what are your alternatives? On the other hand, there might be specific economic advantages to it, primarily related to employment in a certain region with high unemployment rates. That might result in quite different, say, financial or economic performance of the same project. And it's important to realize that the production of your own biomass feedstock requires some very specific organizational considerations. It has to be set up, not just the production, but you also have to consider the potential need for storage of your feedstock, the potential need for transportation from the fields to the energy plants. So that's can be considered as a project in itself. Then the properties of biomass feedstocks, the amount of, let's say, the parameters that you need to have and that you need to know, that depends very much on the type of feedstock. For dry lignocellulosic materials, for example, it's important to know the caloric value, of course, moisture content, ash, and morphology. So basically the size and shape of the material. If you look at biogas feedstocks, you would rather be looking at dry matter, an organic component in your dry matter, the digestibility, the biogas potential, and the carbon to nitrogen ratio, and those are needed to determine its suitability for biogas production. And if you'll be looking at wastewater, it's important to have information on the chemical oxygen demands and the biological oxygen demands, and the solids in suspension and in solution. And these are just, first indications to make your estimates of the energy production potential. There might be other properties that you may eventually need to know to go to a certain design of the system. Where do you get this information? Well, again, there's usually a host of information available from literature, which will give you typical values for different types of feedstock. I think that in the session on feedstock already indicated that there's some very good databases with different properties of biomass, which are freely available. Some information might be available from the company, either from the staff, which you can collect through interview, and maybe information available from documentation. For example, if companies have an obligation to report on their wastewater or their, let's say, other waste production, then this could give you indications of the composition of these types of waste. It might be possible to look at the process as a whole, so that you can see perhaps what quantities of material get converted to final products, and you may get some information on that, on the type of organic material that's will end up in the waste streams. Sometimes you can see that, for example, in the production of wastewater. If you know that's for example the yield of some processes suggests that some amounts of organics end up in the wastewater, then you can make an estimation of what that will mean for the chemical oxygen demand, for example, of that wastewater, or let's say in the end the biogas production potential. And of course, what is quite common is to do your own measurements, take samples and have them analyzed in a lab. Especially if you're carrying out a feasibility study, and this is quite common to assure that the properties of the biomass resource that you have at your availability is actually what you have the properties that you expected. Taking samples is a bit of a craft, so it really takes some thinking. What is important is that you make sure that you know what the sample actually represents. So let's say what comes from. Whether it's let's say taken from the right process, whether it's a fresh sample, whether it's composed of the right flows of biomass, and it's important that you either take the sample yourself, or at least you witness the sampling. So if there's any unexpected outcome from the analysis, that you may have a starting point for the explanation of this. Especially with wastewater, it's very important to realize that the composition of wastewater can vary throughout the day. For example, because some of the processes might be taking place at during some parts of the day, and others may not, and that's important to consider when you take a certain sample, that it might be different from when you take your sample a few hours later. And the second point for wastewater is that you need to be aware of the quantity of wastewater that is being produced at a certain moment. So that you take a sample at some point with certain properties, that it might actually represent a relatively small flow of wastewater with a certain concentration, and that this might not necessarily be representative for the overall wastewater produced by a certain factory or production units. It's important to take the right quantity of sample. It's good to discuss beforehand with the laboratory what amounts of sample they need to carry out their analysis. It's very important to have the right storage conditions and transport conditions of your sample. For example, avoiding the degradation over time. Of course, you need to make sure that the time between sampling and analysis is as short as possible. It's important to keep your samples cooled down in order to reduce the microbial decomposition of the sample over time. And final point is, if you bring your sample to a laboratory, you do need to be sure that the lab that the outcome is reliable, that the laboratory is actually carrying out the test in a proper way, because otherwise your outcome won't be reliable. Yeah, some examples of feedstock properties. For example, if you look at logging residues that you may find in forests, say for example the tops of trees or the branches that are left in the forest when the trunks are taken out. This could be thick branches and tree crowns. Moisture content could be around 40%, especially if the wood has been lying around for a month or two. And for clean wood, your ash content can be limited, can be less than 1%. Another example, fruit waste, mango waste, for example, from fruit juice production, could be composed of the peels and the seed cores and the rejected mangoes. It's usually quite wet material. Some indications of dry matter, organic dry matter, and the CN ratio. Some indications of the biogas production potential per ton of let's say fresh material, wet material, and per ton of organic dry material. Now the logistical issues. Logistics basically concerns the combination of transport, of loading and unloading, and storage required to get biomass feedstock usually from the place where it is produced to the place where it is consumed. Now the complexity of the logistical system and the cost of the logistics can depend very strongly on the feedstock property. So whether it's fluid or solid type of feedstock, and the bulk density, the amounts, of course, the feedstock quantities, the distance that needs to be covered, and the status of the infrastructure, the roads, in some cases rail or even waterways can be considered, and the storage needs in order to assure a continuous supply of biomass, whether that is best done centralized, so near the power plant, or whether it's best done decentralized, so at the place where it is being produced. And lastly, the mode of organization. So let's say who is responsible for example, for the storage, the central, decentral, the loading of the biomass, the transportation of the biomass. You organize that on the side of the consumer or the producer, or you may actually get a specialized transportation logistical company to take the whole chain of logistics for their part. Well, I had another example, but I think we're starting to run out of time. It's included in the presentation, so maybe you can have a look at it. This could be a first assessment of the logistics required, in this case, for the supply of fruit waste from a fruit processing company to a biogas plant at a certain distance for a certain number of days per month and months per year. And this could be, let's say, first assessment of what it could look like, including indications of the costs, the capital expenditures, the operational expenditures, and the cost per ton of material, and how that's to result eventually in the cost per cubic meter of biogas, and the let's see, the amount of energy produced. That is something that I need to modify. Just a moment, please. Well, I'll need to do that later on. Lastly, last remarks on the validation of the feedstock supply in a study, for example. If you need to evaluate the feedstock supply aspects of a bioenergy study, important to first have a look at the properties of the proposed types of feedstock, and whether on the basis of these properties and the suitability of the conversion technology that is proposed is actually proven. So it means whether actually certain, for example, certain type of solid biomass, whether it can actually be used in the gasifier, for example, or whether a certain wet biomass can actually be used for biogas production. Secondly, looking at the overall availability of the feedstock. So on the one hand, the confirmed amounts that are being produced over a extended period of time, preferably, and what quantities are actually being used by the factory that produces it, and if possible, in relation to the production processes of the supplier of the biomass. So to make sure that, in fact, the amounts that are indicated to be available are more or less in line with what you could expect on the basis of the amounts of output being produced by the supplier. Say if you compare it to literature values that could be typical for the industry. Important to assess the inclusion of the logistical system and the infrastructure that may be required for getting the biomass from one place to the other. The cost, whether that is the production cost of biomass, or whether that is the alternative value of biomass to a supplier, or whether it is the logistics cost of getting it from point A to point B. And then consider the potential supply risks, making sure that there is a certain margin between the amount of bioenergy that is required for energy production and the amount that is available, so that in case of let's say low production, there is at least a margin, so that you don't run out of feedstock for energy generation. Having a single supplier of biomass feedstock could provide a certain risk to the supply of the biomass. If you have multiple suppliers and you may have one whose supply is falling short, then this could be let's say the amounts could be taken over by other suppliers, or at least the impact of this quantity, the quantity reduction could be less than when you would have a single supplier. The level of control that you may have over the supply chain. That means you know, if you produce the biomass yourself or buy a sister company, for example, then you may have a higher level of control, and you may be able to make sure that the supply actually comes your way, that it's not suddenly sold to another consumer. And making sure that there might be alternative supplies in case of bioenergy shortages, let's say biofuel feedstock shortages. That's it for today. I don't know if there's any questions on this second part on the feedstock supply assessment.
Bom, caros colegas, antes de terminar, o Bart gostaria de saber se há alguma dúvida sobre esta última parte.
It is not exactly one doubt, but or it is not exactly one question, but I would like to try to understand this in practice. Is it, for example, possible we try to make one exercise considering the feedstock remain from the a market, common market, a municipal market? Is it possible we get one idea and what we can do with the energy from this?
Yes, this is possible. Actually, there are several examples of especially biogas production units that use market wastes as biogas feedstock, although quite commonly in combination with other types of feedstock. I don't know. Do you have any specific case in mind?
Not exactly, but we do have serious problems of waste here in generally here in our towns in Mozambique, and maybe it might be one good solution for this instead of remove the waste from the markets, convert this in energy to be used for other purpose.
Okay. Well, in general, it will need to be removed in any case, because it's not very common that you would have the opportunity of actually producing your energy, in this case, on the same site. Depending, of course, where the market is and what opportunities there might be coincidental nearby to have space and opportunities of constructing a unit. So it means that in such a case you would also be sort of stuck with the logistical requirements. On the second hand, it's especially with market waste, it's important to make sure that it doesn't contain too many contaminations. So if you look, for example, at biogas production, then you should be looking at the easily biodegradable material. From let's say the vegetable, fruits type of waste that you could find. Yeah, the assessment of the quantities is typically something that will need to be measured over longer periods. That can be done, for example, by let's say checking the number of containers that are produced and that are taken away to for disposal, for example. And it's important to check on the different alternatives. On the one hand, with organic waste, you could also use it for composting, for example, which is, well, let's say a simpler, less complicated way of waste processing of biodegradable waste. And you know, there you would have to check whether the potential demand for compost, for example, is such that this might actually fetch a higher value than your potential energy production could, if you would use the same amount of waste and the same type of waste for biogas production, for example. And it's important to realize that the value of the energy production doesn't necessarily be enough to cover the whole cost of the removal, transportation, and pre-processing of the waste. So you might end up with, you know, relatively high production costs, which might have to be compensated by a certain source of income related to the processing of the waste. So you'll be talking about a gate fee, and basically saying, well, you know, municipality, you need to manage this waste. You need to take it out, and the cost for this, for example, will have to be borne by you. So that you make the municipality, for example, responsible for the logistical part, making sure that they deposit it for free at the bioenergy plant, or even asking for a gate fee per ton of material supplied in order to, you know, to get a financially feasible project for energy generation. So those would be the main considerations, and I can see if I can prepare a case study for this. Maybe that could be interesting, but I'd have to see if I can fit it in with the other sessions that we still have coming up. So I'll need to come back to that at a later stage.
Okay.
And of course, you know, if you have a concrete case, then, you know, that could easily even be you know, more valuable. If you know, for example, of a certain, well, we just mentioned market waste. There could also be, you know, other examples. I know that there's plenty of agro processing industries. If you may be aware of particular industries producing significant quantities of byproducts of waste, that could be interesting as case study material. But again, we'd have to check whether we can easily fit in a case study in one of the next sessions.
Okay, thank you from my side.
Okay, thank you, Mr. Fran. I don't know if there's other questions, other remarks.
Haverá mais alguma pergunta, colegas? No. No.
Okay. Well, then I'd like to thank you very much for your attention.